Okay, welcome. We're going to work through some problems from Tuesday. We started looking at these three sections, and Tuesday's class we focused on section 4.5 and 4.6, properties of logarithms, and solving exponential and logarithmic equations. So we're going to start with this, and I wanted to mention that the most important equation is right here, that every logarithmic equation is equivalent to an exponential equation. Really, it's the same thing but in disguise. And this is really powerful if you can just take the three numbers and rearrange them to change the form. So right here, in the exponential side, that's more familiar. B is the base. So that means in the logarithm side, B is the base. And x is the exponent. Right there, exponent. And that means that x in the logarithmic equation, that's also the exponent. And I call y the answer. And we can call it that in the exponential, in the logarithmic equation too. So let's just start rearranging things. Let's go to some basic logarithm facts and see how they're not really that mysterious. Log b of 1, log base b of 1 is 0. Well, b is the base, 0 is the exponent, and 1 is the answer. And so this logarithmic equation is equivalent to the exponential equation that b to the 0th power is 1. And we know that because we're more familiar with exponents. Let's take a look at the one on the right. Log base b of b is 1. Well, the base is b, the exponent is 1, and so this just says that b to the 1 is the answer, which is b. Well, duh. In exponential form, it's so clear, but when we change it to logarithmic form, it's saying the same thing, but it looks a little bit more confusing just because we haven't gotten so used to it. Another way to think about this is the logarithm is asking for the exponent. When we say log base b of 1, we're asking what power of b is equal to 1. And when we say log base b of b, we're asking what exponent of b is equal to b. And so the answers are clear. On the one hand it's 0, the other hand it's 1. So keep that in mind. It's going to come up a lot as we solve these problems. For example, here's the inverse properties for logarithms and exponential functions. The first one, log base b of b to the x is x. And the way I like to write this is that we can bring this exponent, pop it out in front, and we'll end up with x times log b of b. And of course we know that's x times 1, which is just x. And that's what it is. The other one is b to the exponent log base b of x is x. That also looks pretty confusing. What these are saying is that if you take a number x, that's your input, exponentiate it and then take the logarithm, you get x back. So the exponential function and the logarithm function, they undo each other like inverse functions, and that's what they are. And the other way too, if you take a number x, input it into the logarithm function, and then exponentiate it, it has to be the same base, you'll get your number x back. But let's take this and we're going to put it into, we're going to just change form. The first one is log form, and we want to change it to exponential form. So we just have to identify the base. The base is b, the exponent is x, and so this is saying that b to the x is the answer, and the answer is b to the x. So b to the x. All this is saying is that b to the x is b to the x, except there is one subtlety, that this b to the x has been just put into a little box held together. There's your answer, and things fit nicely. So b to the x equals b to the x. Well, let's see what happens with the next one. This is exponential form, So this means that the base is b, and the exponent is a little bit complicated. That's the exponent, and then that means that x must be the answer. So let's just rearrange it. We can change it to log form. Well, this is just saying that log, what's the base? The base is b. What's the answer? The answer is x, equals the exponent, which is log base b of x. What? Log base b of x equals log base b of x? Well, of course it is. That looks so obvious here in log form, but when we put it into exponential form, it looks like it's saying something different, but it's not. It's just obviously true in log form, but it seems something deep and significant in exponential form. And I guess it is. It's just the relationship between a function and its inverse function. Let's go to the next one. Okay, the one-to-one properties for exponentials. One-to-one, we have to remember what this means. This means that if f of x1 equals f of x2, let's say we have two inputs and we get the same output, then it means that the inputs were the same altogether. So for the exponential function, f of x is the exponential function b to the x, and I'm going to draw it right over here. Here's the exponential function. Actually, I can bring that down. Well, I'll leave it like that. The exponential function is going to look like this. That's if b is bigger than 1. If b is less than 1, and it has to be positive, it'll be exponential decrease, but let's leave it like this. If we have this, then we're saying that this function is one-to-one. It's a one-to-one function, and graphically, the way you test it is you use the horizontal line test. And for that, let's get a nice dotted line. Let's go with that. And if you take a horizontal line, it can only cross the function at one point. So there it crosses at exactly 1 point. That's for a y value in the range of the exponential function. If we take a y value that's negative, so outside of the range, it doesn't cross the function at all, and that includes the asymptote y equals 0, no intersection because 0 is not in the range. I want to label that for something that we're going to do later. Let's put a big green dot here. Big green dot, and this is, let's call this the y value m, okay, big M, and here's a point on the function, and the y value is big M. That must mean that there's some x value, let's call it little m. When you input little m into the exponential function, you get out big M, and that just means that big M is b to the little m. That's what it's saying. Little m is the input, big M is the output, and that point is on the curve. And notice it's a one-to-one function, and that just means that if f of x1 equals f of x2, then x1 equals x2. And of course, you can go the other way. If x1 equals x2, just plug them both into the function. You have to get the same output. But what I'm going to do is I'm going to just change the name of these, and let's call it little m and little n, and then the output is going to be mn. So if the input is equal, then the output is equal. But what that is saying is that if b to the m equals b to the n, then m equals n. So long story short, it means that if you have the same base, and the two exponentials are equal, then the exponents are equal. And you can just eliminate the base and just look at the exponents. You can only do that if it's a one-to-one function, and the exponential function, sure enough, that is a one-to-one function. Did you know there's also a one-to-one property for logarithms? And it says pretty much the same thing. If the logs are the same, you have to have the same base, then what's inside the log is the same. You can just eliminate the logarithm. And why is this true? Well, it's because the log function is one-to-one, and in this case, let's draw the log function. It looks like this. If b is bigger than 1, it looks like this. If b is less than 1, it'll be a vertical reflection. But we're just asking, does this pass the horizontal line test? Well, yes, it does. Here's a horizontal line. It only crosses the function one time. Even if it's negative, that's only one place to cross. And let's just do this. Because the range of the log function is all real numbers, the domain is just positive numbers. But I want to put a point there. Let's put a big green point right over here. Let's say that this is y equals, let's use little m here. That means that there's some, actually exactly one x value, big M, so that the input is big M, the output is little m. That means that log base b of big M equals little m, because the function, did I mention the function is y equals log base b of x, or the function itself, log base b of x. But let's go up here and put a rectangle here. Notice that's the log form, but there's an exponential form. Base b, exponent little m, equals the answer big M. And that's just what I had on the other slide. If there's an exponential equation, then there's a logarithmic equation, and vice versa. But anyway, you can see from the graph that the log function passes the horizontal line test, so it's one-to-one, and that means if two numbers have the same logarithms, then those two numbers must be equal. If two inputs have the same logarithm, they have to be the same input. We're going to use that. But let's go to the power rule for logarithms. Here, we want to show that if you take a logarithm of something with an exponent, you can just pop the exponent out in front. And notice that log base b of m to the n, the exponent comes out front, it's n times the logarithm. How do we solve it? Well, this is really a fact about exponents, but disguised as logarithms. And the fact is that if you have b to the m and raise that to the nth power, the exponent rule says that that is b to the m times n. Okay, does that look familiar? It should be, because that's an exponent rule. If it doesn't look familiar, then you got to do some review. But this log rule, the power rule for logarithms, is the same as the power rule for exponents, and we'll prove it. What we're going to do is we're going to use this hint. Notice we're just going to take big M. M must be a positive number because it's an input for the logarithm, and any positive number is the range of an exponential function, so there must be some number little m, which when we exponentiate it is big M. Now, long story short, every number big M is a power of b. And so what we're going to do is we're going to rewrite this log base b of m to the n. Well, I can just rewrite that. That's log base b of b to the m to the n. and I need to put in parentheses, I'm going to emphasize that with parentheses like this. And those are equal because this is just a substitution. Since b to the m and m are equal, I can replace them, replace m by b to the little m. And now I'm going to use the power rule, not for logarithms because that would be circular reasoning. I'm going to use the power rule for exponents. So here we go. We are going to go back to green ink, and this is equal to log base b of b to the m to the n is b to the m times n. Got that? Well, now we're going to use a rule for logs that says log base b of b to the x is just that exponent. Do you remember that? And so we can just use that here. X is m times n. We'll get m times n. But now I need to change that little m back to a big M. And I'm going to do that up here in the corner. That's an exponential form, but the log form is log base, the base is b, and the answer is m, and the answer is little m. That's the log form for m versus m. That means that this little m is equal to log base b of big M. Okay, that's just a substitution. Let me show you that. Whoop, that's a substitution, and that's times n. I'm going to put n in front, and there we go. Let me write down the rule. This is again a substitution. Actually, maybe it's an unsubstitution because it undoes the first substitution with the unsubstitution. But the upshot is that we started with this log base b of a power, and we ended up with this. That's the power times log base b of the number. It's so easy, and we just had to use some basic algebra like substitution and the power rule for exponents and this old rule for logs. Okay. On to the next slide. Here's another of the important rules for exponents. There's top three. The three are the power rule that we just did. Here's the product rule. And then there's going to be a quotient rule. So let's go to this. What we're going to do is a substitution. So we're going to have the same one. Big M is a power of b, b to the little m. And we're also going to use n. N is also a power of b. It's b to the little, how about m? And because we're going to do a substitution and an unsubstitution, let's write this out. That means that little m is the log base b of big M, and little n is the log base b of big, not m, it's n. And that's just the exponential form and the logarithmic form, but that's going to be the substitution because we are going to see the product rule for logarithms is really just the product rule for exponents in disguise. Do you remember the product rule for exponents? It says this. It says that b to the m times b to the n, there's your product. This equals b to the, do you remember? Multiply it, you're going to add the exponents. M plus n. That's it. So there's the product rule for exponents. We're going to use that, and we're going to get started. So here we go. Log base b of mn. We're going to do a substitution, and we're going to get log base b of, well, m is b to the m, and n, big N, is b to the little n. And now we're going to do the product rule for exponents. It's there on the right. And this is going to be log base b of b to the m plus n. Hey, that just is the exponent. The logarithm function says, give me back the exponent, so that's just m plus n. And let's call that a basic rule. Actually, it's not the basic rule. It's an inverse rule for logs. If you take a number, m plus n, exponentiate it, and then take the logarithm, they undo each other, and you get m plus n back. And now we're going to do an unsubstitute. Unsubstitute, little m is just log base b of big M, and little n is log base b of big N. And let's just highlight it. We prove that this equation, the log of a product, is the sum of the logs. Let me tell you a little secret. When I started doing this sort of reasoning, there's a challenge to it. Every little step made sense to me, but it's such a long chain of reasoning that I still had trouble connecting the beginning to the end. But you get better at that after a while. That it's a long chain. As long as every step makes sense to you and you practice this reasoning enough, you'll get to see bigger and bigger chunks and they'll make sense. But at first it's very dense reading and very dense reasoning. Why does this work? But every step has a justification and they connect together and we get the product rule for logs. On to the next slide. The quotient rule for logs. You know, I bet you could do this in your sleep if you remember the product rule for logs. And this is going to depend on the quotient rule for, you guessed it, exponents. Well, the quotient rule for exponents says that if you have the quotient of exponents, you can combine those into one exponent by subtracting. That's it. That's the quotient rule for exponents. And I claim that the quotient rule for logarithms, that's really just the quotient rule for exponents in disguise by a substitution. And here's the substitution. Actually two, because we're going to do both m and n. M is b to the little m. Any positive number m is a power of b. And n is b to the, well, let's use little n. And then the unsubstitution, of course, is that little m is log base b of big M. That's just the logarithmic form of the exponential equation. And little n is log base b of big N. Okay? Those two things say the same thing, but we'll use those to substitute and unsubstitute. So let's get started. We have log base b of m over n. What are we going to do? Well, we're going to substitute. And so this equals log base b of b to the little m over b to the big N. And hey, that's the quotient rule for exponents. So we'll use that. So quotient rule for exponents. And this is equal to log base b of b to the m minus n, because the quotient of exponents is the exponent of the difference. And now this is just m minus n. You know that, and it's called the tip of your tongue. It's the inverse law for logs. It's actually one of them, is one of the inverse logs. And now we can do an unsubstitute, because little m is log base b of big M, and little n is log base b of big N. And we've done it. The log base b of m over n is the log base b of m minus the log base b of n, and that's the quotient rule for logarithms. So now we've done the three basic rules, and I think there's another rule that is important, not as difficult, a little bit more complicated. It's called the change of base formula. And the reason we need this is that your calculator only has 2 log buttons on it. If you're a computer scientist, it might have 3 log buttons on it. But there's the common logarithm, that's base 10, and there's the natural logarithm, base e. So common log is log base 10 of x, but we just call it log of x. We don't even write the 10 because 10 is so common. And there's the natural log, that's log base e of x. E is that natural number. Actually, it's not a natural number, it's Euler's number, and we call that ln of x, which I think is French because they put the adjective on the other side of the noun, so it's logarithm natural. Pardon my French. And here's what we'll do with this. We are going to be able to use the common log or the natural log to compute a number. So let's see, log base 7 of 3, well, that's the base is 7, and m is 3, and for this let's use 10. You can do either one, but let's just do log of 3 over log of 7. And give me a second, I have to get my calculator. Oh, where's my calculator? Here it is. Okay, it's on my phone actually. Let's see, calculator, here we go. And I want log of 3 divided by log of 7 equals, and the answer is 0.5645753. My calculator uses a lot of digits. Actually, it goes on forever, but it cuts off there. And we want 4 decimal places. So we want 1, 2, 3, 4. But we do have to look at 7. The next one is 7. That's big. So we have to round up. And so the answer is going to be 0.5646. That is log base 7 of 3 to 4 decimal places. Okay, now it's time to prove the change of base formula. It's not difficult, just a bit long, but we're going to do this. We're going to use some algebra. What's powerful about algebra is that you can give up, admit you don't know the answer, and then just call it x the unknown, and then work with it. Actually, we're going to call it y the unknown. So I'm going to look at log base b of m, and I'm going to call this y. Because I give up, I don't know what it is, let's just call it y and be over with it. So y equals log base b of m. And that's a logarithmic equation, so I'm going to change it to exponential form. I want to change it to the exponential form. Well, the base is b, the exponent is y, and the answer is m. So that's the equation. And now I'm going to take the common log of both sides. Okay, I can do that. The common log is a function, so I'm going to take the common log of the left side, and I'm going to take the common log of the right side. Those two things are equal. B to the y is equal to m, so when I take the logs, it's still equal, and I'll use log base 10 because that's on my calculator. Actually, to make it more general, it can be log base n for any n that's a base. The restrictions are the base has to be positive and the base can't be 1. So we're going to take the log base n of both sides. You can think common log or natural log. And what we get is is this. The left side, we have that exponent that pops down. You remember that? That rule for logarithms? You don't need to know the name. Is it the power rule? It's the power rule for logarithms. So this is y log of b equals log of m. Okay? Any base you want, base n, base 10, base e. So we get this, and now we want to solve for y. Okay, we're up to solve for y. That means that y equals log of m over log of b. And finally, substitute for y. Do you remember what y was? Here's y. We'll bring that in and substitute right there. And that means that the final form is this equals log base b of m. And of course, I can make the base anything that I want. And that is the change of base formula. Super useful if you want to find, if you want to use your calculator to find the answer. You can use common log or common log natural, ln. Okay, on with our show. Okay, now we're going to solve some problems. We've done the theory, now here's the practice. We want to expand. Well, what I see here is a product, so this is ln of 3ab plus ln of 5c. Okay, because this product becomes a sum. That's what logarithms do. That's really interesting. It turns a product into a sum. But there's more products. There's actually 3 times a times b and then 5 times c. And so I can expand more. This is the natural log of 3 plus the natural log of a plus the natural log of b plus the natural log of 5 plus the natural log of c. And that is quite expanded. Okay, how about this? Next one, expand log base 4 of x over z over w. Well, first I have to say that fraction is looking pretty ambiguous. Is it x divided by z divided by w, or is it x divided by z divided by w? And I can see from the length of the that bar that it's actually x over z divided by w. And here's a quotient, so we can change this to log base 4 of x over z minus log base 4 of w. But there's still another division, so this is log base 4 of x minus log base 4 of z minus log base 4 of w. And that is expanded as much as possible. Last one, the natural log of 1 over 4 to the k. There's a couple of ways to do this. One is you could just write this as the natural log of 1 minus the natural log of 4 to the k. And notice that the log of any base of 1 is 0. And then we can pop out the exponent, k natural log of 4. And so the final answer, it's negative k natural logs of 4. But another way is we could write this as this is the natural log of 4 to the negative k. Because if you have it on the bottom, it's a negative exponent. And we can just pop that negative exponent out times natural log of 4, and we get the same answer, just a slightly different way of doing that. Okay, next slide. More expansion. Expand as much as possible. Okay, so we're going to get, we may as well go step by step. This is the common log. It's base 10. We don't need to write that. X to the 15, y to the 13, minus common log of z to the 19. We keep expanding and expanding. This is log of x to the 15 plus log of y to the 13 minus log of z to the 19. But we can keep on going. We can pop those exponents out. That's just 15 log of x plus 13 log of y minus 19 log of z. And let's put the box around that. Okay, next problem. There's a square root. There's a radical here. Radical notation is nice, but it's awkward when we really need an exponent. So the first thing I'm going to do is I'm going to replace this by y times, and it's going to be y over 1 minus y to the 1/2 power. If you change it to exponent form, things are going to go much nicer. And so we can use the product rule. This is the natural log of y plus the natural log of y over 1 minus y, everything to the 1/2. And it's that exponent, it's this exponent that pops out. It's the exponent that pops out. Where's the exponent? It's there. And so this equals natural log of y plus 1/2 natural log of y over 1 minus y. And now I can use the quotient rule. So this is natural log of y plus 1/2. And I'm going to put in parentheses just to be safe, because it's really, this is one thing, and we're going to group it together. That is natural log of y minus natural log of 1 minus y grouped together. And I can actually expand that. I can distribute the 1/2. It's 1/2 of these and 1/2 of those. And when I do that, I'll actually get two terms with natural log of y. So I'm going to end up with one of them plus 1/2 of them. So it's 3/2 natural log of y minus 1/2 natural log of 1 minus y. And I'm going to put a box around that and just issue a warning that it looks like you might be able to expand this term, but you really can't. I'll put this in red, and with a no over here. This is not the same as the natural log of 1 divided by the natural log of y or anything, because you can't do that. The quotient has to be inside the logarithm. If there's a subtraction inside the logarithm, then we really can't do anything. So that's it. We have the answer, and it's time to move on. Let's go to condense as much as possible. What's the opposite of expand? Well, it's condense. So we're going to try to do these rules in reverse and put things together. And we can do them in any order, but let's do this. Let's put these together. This is the natural log of 2x plus 1 to the 1/2 power. And really, we have to know that there are parentheses there. And let's put these together with the quotient rule. This is the natural log of x minus 1 divided by x squared plus 1. And just to make it explicit, I'm going to put parentheses around those because really those are grouped together. And now I can put these together and get the natural log of 2x plus 1 to the 1/2 times x minus 1 over x squared plus 1, and put that around there. And we could just put our box around there, or if we want to go back to square roots, if you like square roots, this does equal, how about x minus 1 first times the square root of 2x plus 1 all over x squared plus 1. And that is also a valid answer, condensed all into one logarithm. Good skill to expand and condense depending what you want. And next one. Okay, evaluate without a calculator. These ones you don't need a calculator. The first one's hard, the second one's harder. So let's start with the first one. What I want to mention is that the logarithm is really the exponent function. What's the exponent? And it's saying, what exponent of 4 is equal to 2? Well, we know that the square root of 4 is 2, so that means that 4 to the 1/2 is 2, and so the exponent that we want is 1/2, so 1/2 is the answer. If you found that complicated, here's the method where you admit defeat first and then change to exponential form. Okay, I admit defeat. I don't know what the answer is. I am going to call it x, the unknown, and I'm going to change to exponential form because that's in logarithmic form, and this just says that 4, the base to the exponent, is equal to 2, and I have to know what that is. And one thing I could do, let's move this out of the way, is I could change to the same base. I could change this. 4 is the same as 2 squared. And this means I really have 2 to the 2x equals 2, and 2 is 2 to the 1. And here's where you have the one-to-one property. This means that 2x equals 1. If the exponentials are the same, then the exponents are the same. So x is just 1/2, and there we go. 1/2 is the answer. So a lot of ways to do this, but getting used to using those logarithm rules helps a lot. Being able to change between logarithm and exponential form, that also helps a lot. Okay, let's do number 22. Oh my goodness. Log base 5 of e to the -2 natural log of 5. We have to evaluate without a calculator? Well, here's one thing. You got to do something. And I can do something in the middle, right there, in the innermost part. This is the natural log of 5 to the -2. Right? And if I just leave everything else the same, it's going to be e to that. And I want log base 5 of e to that. And now we're talking, because over here, this is just the inverse property of exponentials. Logarithm, the natural log is base e, so what I've done is I have 5 to the -2, I take the logarithm, and then I exponentiate. Those undo each other, so that whole thing is 5 to the -2, just working from the inside out. And so what I have really is log base 5 of 5 to the -2, and again, the inverse property of log says it's just -2, and that is the answer. Who knew? This was such a setup problem to test, do you know that one rule? And if you do, it's a lot of fun. If you don't remember that rule, then it's like banging your head against a brick wall. Don't do that. Okay, another thing we can do without a calculator is this one, because we're going to change so that they have the same base. And notice that 625 is here in this sequence, and 125 also. This is just 5 to the 0, 5 to the 1, 5 squared, 5 cubed, 5 to the 4th, 5 to the 5th. If you remember your powers of 5, this would be clear, but that's the pattern. Not everyone can keep doing it. When we were kids, you probably doubled numbers, but did you multiply them by 5 over and over again? Probably not. So what we have, this is 5 to the 4th power times 5 to the 3x plus 3 equals 5 cubed. And I can combine these with the product rule for exponents. This is going to be 4 times. I really need parentheses here. I have to remember that I have parentheses. It's 3x plus 3 equals 5 to the 3. And we're going to use a one-to-one property. If if the exponents are the same, then the exponents are the same. If the exponentials are the same, the exponents are the same. But this just means that 4 times 3x plus 3 equals 3. And let's do this a clever way. Notice there's a common factor here. That's 3x plus 1. So I have 4 times 3 times x plus 1 equals 3. 3 is 3 times 1. And I can cancel out the 3. And this brings us up here. 4 times x plus 1 is 1. That means x plus 1 is 1/4. That means that x is 1/4 minus 1, which is 4 over 4. So x is negative 3 over 4. That is the number x. So when we have the same base, the key to that was using the one-to-one property to turn an exponential equation into a linear equation. And then it's not so bad. We can't always use the same base situation. In that case, here's an example of what to do. This is an exponential equation, and what I'm going to do is I'm going to take the log of both sides. And that's generally the case. If you have two sides that are equal, you can do the same thing on both sides and it's still equal. And I'm going to take the log of the left side, and that'll equal the log of the right side. And it can be any log, any base you want. Why not the common log or the natural log, because those are on the calculator. So this is 2 to the x plus 1 and 5 to the 2x minus 1. And notice that we have exponents. The exponents are going to pop out in front. And I wish I could animate that. Wouldn't that be cool? So we have x plus 1 log of 2 equals 2x minus 1 log of 5. This still looks kind of scary, but remember that log of 2 and log of 5, they're just numbers. So what I'm going to do is I'm going to distribute those factors, and I'm going to get x times log of 2 plus 1 times log of 2, and times log 5, that's 2 log 5 times x minus log of 5. And this takes us back to the beginning of solving equations, and that's really just collect like terms. So I'm going to put all of the x's on one side, all of the non-x's on the other side. And if I do that, I'll have x log 2 minus 2 log 5x equals a negative log of 2 minus log of 5. And on the left-hand side, notice there's a common factor, x. So that's log x times log 2 minus 2 log 5. And I can take this up here and find that finally, by dividing, x is, in the numerator, negative log of 2 minus log of 5 all over log of 2 minus 2 log of 5. And this is something that you could do in your calculator if you wanted to, if you were asked to do that, if you had time. But otherwise, let's just put a box around it and say that we're done. On to the next problem. Solve this. Okay, I think we're at the end. This is our last problem, and thanks for bearing with me. This is a hidden quadratic. Well, not so exciting, but really, this is a quadratic because I want you to notice something, that e to the 2x, that's the same as e to the x squared with the power rule for exponents. And so what we really have in this equation, is we have e to the x squared minus e to the x, and I'll put parentheses around that too, minus 6 equals 0. And what I'm going to do is I'm going to substitute e to the x. Let's just give that a name. How about big T? So this is really big T squared minus big T minus 6 equals 0. And that's the hidden quadratic. We can solve this one by factoring. We don't need to use the full-blown quadratic formula, but here's a t, here's a t. 6 is 2 times 3. One of them is positive, one is negative. It's going to be negative 3, positive 2. And so this means that t is negative 2, or t is positive 3. Those aren't the answers yet because we did a substitution, and we have to undo the substitution. This means e to the x is negative 2, or e to the x is 3. And this second one, that's fine. That's let's just change that to log form. X equals log base e of 3, or you can say x equals the natural log of 3. That's the answer from there. But what about this other one? This other one, there's actually no solution. And that's because negative 2 is not in the range of e to the x. Quick picture. Here's a picture of e to the x. Let's draw this in purple. E to the x looks like this. And negative 2 is down here somewhere. So if I try to find the connection, here's negative 2. Negative 2 is never an output for the exponential function. So there's no solution there. One other thing about this, if we did solve it, you would get, I'm going to put this in red because we're not supposed to do this, you would get x equal the natural log of negative 2, and in that case, negative 2 is not in the domain of the natural log of x, because the natural log of x is it's the inverse function of the exponential, so it looks something like that, and negative 2 would be here. It's not in the range. It's not a valid input for the logarithm function. We've come to the end of our slides. Thanks for bearing with me, and I'll upload this to YouTube, get it on Google Classroom, and I'll see you in class for some applications. Thanks so much.